Okay, so a linear function or linear equation in two variables that's written in this form where x and y are on the same side of the equation is said to be in standard form. And then if we were to take the time and solve this equation for y, we could hammer this into a very popular form for linear equation called y equals mx plus b form. This is called slope-intercept form. All right, slope-intercept form is a very popular form for a linear equation in x and y because we can just read off the slope of the line, which is this number m being multiplied by x, and b is the y-intercept. The y-intercept being the point of intersection between the graph and the y-axis. So this is called slope-intercept form here. And like I said, it's a very popular form for the linear function here. Okay. All right. So the first thing we're going to do is we're going to address how to graph a linear function 2x plus 3 in the xy plane. Okay. And there's many ways to graph a linear function in the xy plane. We are going to look at a couple of different ways here. The first method that you normally run into in early algebra is the table method. Okay. So we'll look at that technique first. And as the name suggests, we're going to construct a table here. The first column will be called our x column. The second column will be the y column. And I like to have a third column, which is my ordered pair column x comma y. Solutions to linear equations in x and y are going to be ordered pairs. Of course, the x coordinate would replace the x variable and the y coordinate would replace f of x. That's another name, by the way, for y. Okay. And we like to choose some nice values for x, try to keep them close to the origin for plotting purposes. You don't want to choose something too far away from the origin because it's going to make life miserable in trying to plot the point. Okay. All right, now in the word linear, there is the word line that's embedded in this word. For that reason, we're going to discover that the graph of a linear equation or a linear function is always going to be a straight line in the xy plane. And because of that, it suffices, bare minimum, to have two unique solutions, ordered pair solutions or points, to determine a unique line in a plane. I like to plot more than 2 points. 3 points is better than 2 points, but you bare minimum, you can get away with plotting 2 points to determine the graph of a linear function. I'm going to choose x to be like -2, 0, and then positive 2, okay? So if x is equal to -2, to find y, y being f of x, y is really going to be my function f of x evaluated at -2. Which means I put -2 in for x. So f of -2 is going to be 2 times -2 plus 3. And therefore, 2 times -2 is -4, plus 3 nets us -1. Hence, one ordered pair solution to this linear function is going to be -2 comma -1. That's going to be a point that would lie on the graph of this linear function here. I'm now going to choose x to be 0, and if x is equal to 0, we need to find what the y coordinate would be. To find that, we're going to evaluate our function at 0, which means I put 0 in for x. So we got 2 times 0 plus 3, which means 0 plus 3, which means 3. So therefore, if x is 0, y must be 3. Hence, we have another ordered pair solution for that linear function, which would be 0, 3. So 0, 3 would have to be another point that lies on the graph of this function. Finally, if we let x be equal to positive 2, y is going to be equal to the function evaluated at 2, which is to say 2 times 2 plus 3, which is to say 4 plus 3 or 7. So we have another point we can plot that would also lie on the graph of this linear function 2, 7. That should be more than enough ordered pair solutions or points to determine the unique graph of this linear function in the plane. So what I will do now is take a piece of graphing paper here, and I'm going to plot these points in the xy plane. Of course, this is your y-axis, this is your x-axis. Plotting -2, -1, we start at the origin, and I move 2 units to the left on the x-axis, -1, -2, and then I move down 1 unit parallel to the y-axis, -1. So -2, -1 is a point that finds itself in the third quadrant. Plotting 0, 3 rather, we start at the origin. I don't move right or left because my x-coordinate 0. I just move up 3 units on the y-axis. So 1, 2, 3, there's 0, 3. Another thing you can do, you can label these points if you want to. It does tend to clutter your graph up, but if you make them small enough, it's really no big deal. Finally, plotting the point 2, 7, we start at the origin. I move 2 to the right and then up 7 units parallel to the y-axis. So 2 to the right, 1, 2, now up 7. 1, 2, 3, 4, 5, 6, 7. 2, 7 would be right here in the first quadrant. Take a ruler now and put a line through those points, ladies and gentlemen, as it does appear that these lines are collinear points in the sense that they lie on a line, and that has to be the case because the graph of a linear function must always spawn a graph that must be a line. Therefore, I'm going to put a nice line through these points, put arrows at the end of my line, and we are done. We have the graph of that linear function, f of x equals 2x plus 3. That would be its graph. And any point that lies on this line would be a solution to this function or would satisfy this linear function. Any questions how I graph that linear function using the table method? And okay, so that's one way to graph that linear function. Alrighty. Does that make sense how we did that there? Okay. So table method involves making a table, choosing some values for x, computing what the corresponding values for y should be, plotting the points, putting a line through the points, and you have the graph. All right. Okay, any questions about the table method for this one right here? All right, another popular way to graph a linear function is to use what is called the XY intercept method. Okay. So graphing by XY intercept. First of all, what is an X and Y intercept of a graph of a relation or a function? Well, suppose I graph a linear function and its graph is this line in the XY plane. There's usually 2 points of big interest to us. The first point is the point of intersection between the graph and the y-axis. This point of intersection between the graph and the y-axis is called the y-intercept. The y-intercept. The point of intersection between the graph and the x-axis is called the x-intercept. Now, a y-intercept is always a point that must lie on the y-axis, and therefore, being the case, its x-coordinate must always be equal to 0. Because if the x-coordinate's not 0, the point is not going to be on the y-axis. It'll either be to the right or to the left of the y-axis. In a similar fashion, to qualify as being an x-intercept, the point must lie on the x-axis. Therefore, its y-coordinate has got to always be equal to 0. Because if the y-coordinate's not 0, the point will not be on the x-axis. Okay? So in general, this shows us how to find x and y intercepts. To do so, you just set the other variable equal to 0. Any questions about x, y intercepts? All right, so here we're going to do this. We're going to try this out. We're going to try to graph the linear equation 2x plus 3y equal to 12. We're going to graph it not by the table method this time, but we're going to try to graph it by the XY intercept method. And therefore, we're going to have to find the x and y intercept. Let's find the x-intercept first. What do I set equal to 0 always to find an x-intercept?
The y value.
Y coordinate gets set equal to 0. Take 0, substitute it in for the y variable into the equation, and then we'll solve the equation for x. Hence, our equation, linear equation, becomes 2 okay, becomes 2x plus 3 times 0 equals 12. And now we're going to solve this equation for x to get our x-intercept here. Okay. All right, so how do we solve this equation for x? Well, we have 2x, 3 times 0 is 0, that's gone. So 2x equals 12, divide both sides by 2, and my x-intercept appears to be 6. Or as an ordered pair, it would be 6, 0. That's my x-intercept. So this is going to be the point of intersection between the graph of this linear equation or linear function and the x-axis. Now we'll compute the y-intercept. And to find the y-intercept, what do I always set equal to 0? To find the y-intercept, we always set x equal to 0. Okay. So let's let x be 0, take 0, substitute it in for the x variable into the equation, and then we'll solve for y. And now we have to solve for y. 2 times 0 is 0, that's gone, so we have 3y equals 12. Divide both sides by 3, and it appears that our y-intercept is going to be 4. So that would be your y-intercept, 0, 4. Questions how I computed the x and y-intercepts for this linear function or linear equation in x and y? Any questions how I computed the x and y-intercepts? All right, next step now is to plot those points and put a line through the points, and we will have the graph of this linear equation. So let's take a piece of graphing paper and do so. All right, so therefore I am going to plot my x-intercept, which is 6, 0. Start at the origin, and I move 6 to the right and stay on the x-axis. 1, 2, 3, 4, 5, 6. There's 6, 0. And again, feel free to label the point if you want to. It does clutter your graph up a little bit, but it's nice to, do that if you're able to do that. That's my x-intercept. Now I'm going to plot my y-intercept that I found for this linear equation. My y-intercept was found to be 0, 4. So to plot 0, 4, we start at the origin. I stay on the y-axis and move up 4 units. 1, 2, 3, 4. There's my y-intercept. Take a ruler, connect those 2 points with a straight line, and you have the graph of that linear equation in x and y. And that would be the graph of 2x plus 3y equals 12. Any questions how I graph this linear equation by using the x-y intercept method? Does that make sense there? So that's another popular way to graph a linear equation or function, is to compute its x and y intercepts. Any questions about that method there? Okay. All right, ladies and gentlemen, there is another way to graph a linear equation. It's called the slope-intercept form method, where we get our equation into what's called slope-intercept form. But before we do that, I think it would be wise to maybe review what the slope of a line is in the XY plane, okay? So that's the next thing we're going to look at, is the slope of a line in the XY plane. And we'll come back and show you yet another way to graph a linear equation or linear function using the slope-intercept form. But first, maybe we should jog our memory as to what the slope of a line is all about. All right, suppose that I have a linear function and I graph it, and suppose that it, is a line that maybe looks like this. I'm going to choose 2 unique points on this line. This point here is going to be called my point x1, y1, and this point is going to be labeled as x sub 2, y sub 2. These are called subscripted variables, x sub 1, y sub 1 versus x sub 2, y sub 2. What I'm going to do is I'm going to drop this point vertically down to the x-axis, and it would strike the tick mark on the x-axis, which is x sub 1, because that's the x-coordinate of this point. Similarly, dropping this point vertically down to the x-axis, it would strike the tick mark of x sub 2 on the x-axis, because that's its x-coordinate. Projecting these points horizontally back to the y-axis, project this one back over here, it would strike the tick mark of y sub 1. Projecting this point back to the y-axis, it would strike the tick mark of y sub 2. Do we understand this picture so far? I'm now going to build a little right triangle here. And here would be a 90-degree angle, or called a right angle. So I have a little right triangle here. Everybody see the right triangle? All right, now slope. What is it? Well, in a crude sense, ladies and gentlemen, the slope is the measure of the amount of rise we experience versus the amount of run we experience as we move from one point on our line to some other point. But what is this thing called rise versus run? We would like to become more mathematically precise in what we're saying. And so therefore, suppose that I walk from this point x sub 1, y sub 1 up to this point x sub 2, y sub 2 along this line here. Okay, so I walk from this point up to this point. How much rise do I experience? How much vertical change do I experience in going from this point up to this point? Well, the amount of rise I experience is going to be represented by the difference between the y coordinates of these 2 points. This is the amount of rise I experience, which is going to be y sub 2 minus y sub 1. That's the amount of vertical change I experience in walking from this point up to this point along this line. But I'm also simultaneously going to be experiencing horizontal change in my location. How much horizontal or how much run do I experience in walking from this point up to this point along this line? Well, the amount of run I experience, or the amount of horizontal change I experience, is going to be represented mathematically as the difference between the x coordinates of these 2 points. Namely, this is the amount of run I experience, which is going to be x sub 2 minus x sub 1. And there we go. So therefore, ladies and gentlemen, the slope of this line is going to be the ratio of the amount of vertical change to that of the amount of horizontal change I experience as I move from one point to another point on this line. So therefore, I have developed my slope formula. And this would be the slope formula. And by the way, in all textbooks that you'll ever look at in mathematics, they always use m for the slope. So therefore, the slope of a line given 2 points on a line is going to be equal to the difference between the y coordinates of the point divided by the difference between the x coordinates of the 2 points in question. This is called the slope formula. It will enable me to compute the slope of any line just so long as I have 2 unique points on the line. All right. Do you remember having seen this formula somewhere in your past? This being college algebra means that you've had to have algebra somewhere in your past. And there's no escaping the slope formula in either elementary or intermediate algebra here at Mott Community College. You should have been exposed to this. All right, so here we go. We're going to put it to use. We're going to try to find the slope of the line that contains 2 points, -3, -8, and the other point will be 4, 6. So suppose that a line goes through these points in the xy plane or contains these 2 points. We want to compute the slope of this line. Well, there's a couple different ways of doing it. You can do it using the slope formula, or you can do it visually by plotting these points in the xy plane. I'm going to compute it first by using the slope formula, and then we'll maybe turn it over to the xy plane and convince ourselves we get the same slope. Now, it doesn't matter which point you designate as being your first and second point here. That's entirely up to you. So I'm going to call this maybe my first point, x1, y1, and I'll designate this as being my second point. But it doesn't matter. You could have called this your second point and this your first point. It doesn't matter. You'll get the same slope if you do things correctly. So the slope of this line is going to be the change in y over the change in x. y2 minus y1 over x sub 2 minus x sub 1. And we call this, there's a more compact way of representing the change in y. It's by using this little triangle here. This triangle means the word change. The change in y over the change in x. This is notation that you will see in your first semester of calculus, okay? So this little triangle means change. The change in y over the change in x represents the amount of rise versus run, which is called the slope of a line. All right, what do I plug in for y2 based on how I label my points? What goes in for y sub 2? What drops in?
6.
6. 6 drops in for y sub 2. So we have 6 minus y sub 1. Y sub 1 is -8. Be very careful with your signs when using the slope formula, as those are the most common mistakes, is messing up the signs. Divided by the change in the x coordinates, x sub 2 minus x sub 1 would be 4 minus a -3. And therefore, 6 subtract a -8 is 6 plus 8, which is 14. And that's over 4 subtract a -3, which is 4 plus 3, or 7. And you can even reduce this down to 2 over 1 if you want. Okay? So therefore, the slope of this line that contains these 2 points appears to be 2 over 1, with a rise of 2 and a run of 1. So this is one way to compute the slope of this line by using the slope formula. Any questions how I computed the slope of that line using the slope formula? Okay, another way to determine that slope is to determine it graphically by using a piece of graphing paper. So I will plot the points -3, -8, and 4, 6. Let's plot those points. So -3, -8, I start at the origin. I go 3 to the left, -1, 2, 3, and then down 8. -1, 2, 3, -4, -5, -6, -7, -8. There would be my point -3, -8 in the third quadrant. All right, so that's my point -3, -8. Plotting the other point, which would be 4, 6. We start at the origin, and I move 4 to the right. 1, 2, 3, 4, and now up 6. 1, 2, 3, 4, 5, 6. There would be the point 4, 6. You can connect those 2 points with a line using a ruler, and you would have the graph of that line that contains these 2 points. Now we can determine the slope of this line visually, if you will, using our graph. So suppose, ladies and gentlemen, I want to walk from this point up to this point. So I'm going to walk along my line this way. How much rise do I experience and how much run do I experience? Well, the amount of rise I would experience is going to be represented this way. That's the amount of rise I would experience. And how much rise is that? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Plus 14 units of rise. How much run in walking from this point to this point on the line do I experience? The run is going to be in the positive x direction. The amount of run is going to be in the positive x direction. Positive 1, 2, 3, 4, 5, 6, 7. Positive 7. There you go. So therefore, the slope of this line we can clearly see is plus 14 for the amount of rise divided by the amount of run, which is plus 7. Or you could reduce this down and say plus 2 over 1 is the slope. So the slope is 14/7 or 2 over 1. Why could I call it 2 over 1? Well, look at, I could go from this point to just this point. I could walk along my line from this point to this point. How much rise do I experience? That would just be what? 2 units of rise. And how much run do I experience? Plus 1 unit of run. Up 2, 1 to the right. Slope is 2 over 1. Same as 14 over 7. Okay. Or, ladies and gentlemen, are there any other ratios that are equivalent to 2 over 1 or 14/7? You agree another ratio that would be equivalent to 2 over 1 would be what? 8 over 4? Isn't that true? So another way you could view the slope of this line is to say it's 8/4, which is really 2 over 1, which is really 14/7. So I could have started at this point, and I could have went up 8 units. 1, 2, 3, 4, 5, 6, 7, 8. And then I could have went 4 units to the right. 1, 2, 3, 4, and I'll be darned if I don't land on that same line. Do you agree? So I could have went up 8 units. That would be my rise, and then my run would be positive 4. 8 over 4 is the same thing as 2 over 1, is the same thing as 14 over 7. Is this getting through and making sense here? Or check this out. What if I was at this point, I decided to walk down this line from this point down to this point? Now what would be my rise? My rise now is going to be not positive 14, but it's going to be what? It's going to be negative 14 because I'm going in the negative y direction. And my run would be not positive 7, but it would be negative 7 because I'm going in the negative x direction. But ladies and gentlemen, you agree that negative 14 over negative 7 is the same thing as positive 14 sevenths, which is the same thing as 8 fourths, which is the same thing as 2 over 1. So, you know, whether you call the slope 14 over 7 or negative 14 over negative 7, or you call it negative 2 over negative 1, or you call it negative 8 over negative 4, guess what? These are all equivalent to each other. Okay? Is this making sense how we determine the slope of that line visually, graphically? All right, now we can get back to showing you how to graph a linear equation using another technique called the slope-intercept form. So I showed you how to graph a linear equation using the table method, the xy-intercept method, and now I'm going to show you how to graph a linear equation using the slope-intercept form method. So suppose that I want to graph, let's say negative 6x, okay, plus 3y equals, let's say 12, okay? And I want to graph it this time, not using the table method, not using the xy-intercept method, which I could use any of those methods, but I want to use a different method this time. I want to graph by the slope-intercept form method. Slope-intercept method. So to graph by using the slope-intercept method, I have to get this equation, solve for y. So solving for y. How do I solve for y? How do I solve this equation for y? How do I get this equation, which presently is in standard form, ax plus by equals c form? How do I get it into, from standard form, how do I get it into slope-intercept form? That's what I'm trying to do here.
Add the 6x to the other side.
Let's add 6x to both sides, exactly. So we add 6x to the left, and I add 6x to the right. 6x's drop out on the left, leaving you with 3y. Now I'm going to flip these terms around because I'm shooting for slope-intercept form. So I'm going to say 6x plus 12, same thing. Now to solve for y, we divide both sides by 3. Which means I got to divide both terms on the right side by 3, meaning this gets divided by 3 and this gets divided by 3. Therefore, y equals, this reduces down to 2x plus 12 divided by 3 reduces down to 4. Well, ladies and gentlemen, I now have gotten my equation from standard form into a very special form called what? That's called slope-intercept form. Do you agree? And what's the significance of having this equation in slope-intercept form? Well, the significance is we can read off the slope of the line. The slope of the line is 2. So the slope is 2 over 1 or 2, and b is the y-intercept. So the y-intercept of this line, we can read it right off from the equation, is 4. Do you think this is enough information now, knowing the slope and the y-intercept, to graph this linear equation? Do you think we have enough information?
Yeah.
Yeah.
We have enough information to graph this linear equation, because knowing the y-intercept and the slope is enough to do so. Let's demonstrate how to do that now. Okay, so what I'm going to do is I'm going to take a piece of graphing paper. I'm going to plot the y-intercept, which is 4, or as an ordered pair has to be 0, 4. That would be the y-intercept. And then using the slope, 2 over 1, a rise of 2, a run of 1, we should be able to plot more points on the line. So plotting the y-intercept, 0, 4. Go to your xy plane here. Plotting 0, 4, we start at the origin. I stay on the y-axis and move up 4. 1, 2, 3, 4. There's the y-intercept. 0, 4. And now to plot other points on this line, all we have to do is navigate from our y-intercept. We just have to navigate up 2 units and 1 unit to the right in accordance with what the slope of the line is. Okay, so therefore, if I start at my y-intercept, if I go up 2 units, up 2, now 1 to the right, I should be able to plot another point on my line. I can do that again. Up 2, 1 to the right, plot point. 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 You could do this forever. Or, ladies, what's another name for positive 2 over positive 1? You agree I could have just as well viewed this slope as being negative 2 over negative 1? In which case I could start at my y-intercept and go down 2 units and 1 unit to the left. I would land on the same line. Let's try that. Start at the y-intercept, go down 2 units, 1, 2, and then 1 unit to the left. Guess what? Same line. Down 2, 1 to the left, plot point. Down 2, 1 to the left, plot point. All these points are collinear points. They have to be because this is a linear relationship. And linear functions have straight line or line graphs. Connect the points with the line and we are done. We have the graph of negative 6x plus 3y equals 12. Any questions? How I graph this linear equation or function by getting it into slope-intercept form. And then plotting the y-intercept using the slope to plot other points. Everybody understand how we just graph that using the slope-intercept form? So I showed you 3 different ways of graphing a linear equation. Table method, xy-intercept method, and then the slope-intercept form method. All right. Any questions here so far? All right, let's get back to that thing called slope. The slope of a line is the measure of the amount of rise versus the amount of run you would experience in moving from one point to another point on the line. And this is a well-known fact. If you have a line, which is a graph of a linear function, and suppose that that line graph looks like this. As we progress from left to right in the plane, notice we would be rising on this line. We would be moving upwards. We call this a rising line. So any linear function or equation that has this type of graph where it's oriented this way, we say is a rising line. And it's a well-known fact, ladies and gentlemen, that rising lines always have positive slopes. So the slope of a line that would be oriented this way better have a positive slope. That's always the case. Contrast that with the graph of this linear function. And this would not be a rising line now. This is called a falling line. Because as you progress from left to right in the plane along the line, you're falling down on the line. Okay, the x coordinates, the y coordinates are decreasing. Falling lines always have negative slopes. So the slope of a line oriented this way better always have a negative slope. There's 2 other scenarios. If you graph a linear function, suppose that the graph is a vertical line. And by the way, a linear function that has a vertical line graph, its equation would be x equal to c, where c is some real number, and the graph of this vertical line would go through the x-axis at c. What's the slope of a vertical line? Suppose I choose 2 unique points on this vertical line, and I navigate from one point to another point along the line. I have a question for you. Would I have any run taking place as I move from one of these points to another point? Any run?
No, only rise.
Only rise. And because it's only rise, ladies and gentlemen, think about it. Because there's only rise, the run would be 0. Okay, so what happens when you divide a real number by 0? It's always called what? When you divide something by 0, it's always called undefined. You cannot divide anything by 0 in mathematics. So the slope of a vertical line is always undefined. Undefined slope. Vertical lines have undefined slopes. All right, one last scenario. Suppose that I graph a linear equation that just has the y variable, y equal to some real number c. Well, the graph of such a linear equation as this is going to be just a horizontal line that goes to the y-axis at this number c here. Suppose I choose two unique points on the horizontal line and I navigate along the line from one point to another point. As I do that, do I experience any rise? Any rise?
No.
There's no rise. It's all run. Do you agree? And so therefore, because our slope formula is rise over run, all right, there is no rise. It's all run because we're on a horizontal. So the rise would be 0. And what's 0 divided by any non-zero real number? 0 divided by any non-zero real number is what? 0. So the slope of a horizontal line is always 0. So there you go. When you graph a linear function, its slope has got to be one of these four scenarios. Either it has to be a positive slope for rising lines, negative slope, falling lines, vertical lines have undefined slopes, and horizontal lines always have a 0 slope. Kind of makes sense that a horizontal line has no slope. Some students say no slope, which is okay. Technically, you're correct when you say no slope because that means there's 0 slope. Because if there's a line or a surface that has no slope, it's a horizontal line or surface. I mean, if you're going to try to do downhill skiing on a horizontal slope, you're not going to be doing downhill skiing because you're not going to be going down or up, right? It's horizontal, it's level. There's no slope to it. Any questions so far here? Does slope have any meaning in the real world, ladies and gentlemen? Or is this something that we just cook up just to make sure that we stay off the streets on a Saturday night? Oh, it has meaning, it has relevance. Let me paint you a picture as to where it would have any relevance. In fact, I'm just going to show you the example instead of writing it down. I already wrote this in my lecture notes here. Let's entertain this example. Suppose a car travels a distance of 20 miles in 1 hour, and it travels 60 miles in 4 hours. Find the average speed of the car. So what's the average speed of this car in miles per hour? Well, we're going to find out later on that slope is a rate of change. It's a rate of change of the y variable with respect to the x variable. Slope is a rate of change. All right. And so I have two ordered pairs here. If you consider my horizontal axis as being like the time axis and my vertical axis being the distance axis, I have two unique points. 1 hour after this car leaves its starting position, it will have traveled 20 miles. So my x coordinate is time, my y coordinate is distance in miles. Time is in hours. I have another point on my line, which is, I'm going to call x sub 2, y sub 2, which is 4 hours after this car leaves its initial starting point, it will be 60 miles down the road. All right, I now have two unique points that sit on the graph of this distance time relationship here. I should be able to find the slope, therefore, of the graph of this distance time relationship between the car and distance and you know, the car, the distance, and the time. So I will use my slope formula. I got two unique points. I should be able to, you know, throw things into the slope formula and crank out the slope of this line here. Based on how I labeled the points, the change in y will be 60 miles minus 20 miles, divided by the change in x, which is the change in time, which would be 4 hours minus 1 hour. Therefore, the average speed that my car will be traveling on this time interval from 1 to 4 hours, my average speed will be 40 miles per every 3 hours, which is approximately about 13 miles per hour. Not exactly. This is approximately. I rounded off. 13 miles per hour. That would be the average speed of my car. 13 miles per hour. So slope does have a lot of meaning in our everyday lives. It's a rate of change of one variable with respect to another variable. In this case, it's the rate of change of distance versus time, which we know better as speed, or the rate with which a vehicle or object is traveling. Does that make sense? How slope can be applied to the real world, ladies and gentlemen? Okay. And you get into calculus 1, ladies and gentlemen, you're going to become even more sophisticated because we're talking about this being the average speed of 13 miles per hour. So I have a question for you. Does that mean if this is the average speed of 13 miles per hour on a time interval for 1 to 4 hours, I was driving that speed constantly at all times between 1 and 4 hours? Do you think that's what it's saying? If I got to get on the expressway and I say my average speed over a 3-hour journey is 60 miles per hour, does that mean I was constantly driving 60 miles per hour at all times? Anybody want to weigh in on that situation?
No,
My average speed is 60 miles per hour. Does that mean I was driving precisely 60 miles per hour at every instant in time?
no,
The answer is no. That's just an average speed. I could have been driving 80 miles per hour at one moment in time, or I could have been driving only like 40 miles per hour at another instant in time degree. That's my average speed, ladies and gentlemen. All right. Algebra can deal with average rates of change of functions with respect to the independent variable, but it cannot deal with instantaneous rates of change. If I wanted to know my instantaneous speed at one moment in time, precisely, let's say at the 1.5 hour mark, at that one instant in time, what was my speed? That's called the instantaneous speed. Algebra cannot deal with instantaneous rates of changes of functions with respect to an independent variable. It can only deal with average rates of change. There was a branch of mathematics created to deal with instantaneous rates of change. That branch of mathematics, ladies and gentlemen, is called calculus. Integral and differential calculus was developed to basically address what is the instantaneous speed of an object precisely at one moment in time versus what's the average speed of an object on a particular time interval. All right. For instance, if a rocket blasts off from a launch pad, its speed is constantly changing versus time. Do you agree? As the rocket is constantly accelerating faster and faster as it moves upwards into space. Well, ladies and gentlemen, suppose I wanted the precise speed of that rocket, okay, exactly 3 minutes after launch. At the 3-minute mark, what if I wanted the speed of that rocket? Well, algebra cannot answer that question. Calculus can answer that question, okay? What is the precise instantaneous speed exactly at the 3-minute mark? Calculus was designed to deal with and work effortlessly with variables that constantly change through time, okay? That's why the calculus was developed. It can answer questions that algebra cannot answer. Okay. All right, so slope has applications in the real world, ladies and gentlemen. Okay, the next thing I would like to address is the concept of parallel versus perpendicular lines. Does anybody want to tell me what parallel lines are? We say two lines are parallel if what? Anybody? Parallel lines.
Two lines that go in the same direction.
Yes, they go in the same direction. In fact, not only do they go in the same direction, but they will never ever do what in the XY plane? They will never
Intersect.
cross or intersect each other. They're called parallel lines. So think about it. What do you think has to be true about the slopes of parallel lines if they never are to touch each other in the XY plane?
Same slope.
They're
They
the
have
same
to have,
slope.
yeah, the slopes have to be identical, because stop and think, if one of the lines has a slightly different slant or slope than the other line, eventually it's going to what? Cross it somewhere. Do you agree? So to be parallel, the slopes have to be the same. So therefore, if I call this line 1 and line 2, and if I say that line 1 is parallel to line 2, notice the symbolism. Line 1 is parallel to line 2, then it must be true then that the slope of line 1, which I'll call m sub 1, had better be equal to the slope of line 2, which I'll call m sub 2. Parallel lines have equal slopes. That's what this is saying. Okay? You are correct. They have to have the same slope. How about perpendicular lines? What are perpendicular lines? Can somebody describe for us what perpendicular lines are? Do perpendicular lines intersect in the plane? Do they cross anywhere?
Yeah, they,
Yes, they do. But look, there's a lot of lines that cross. These two lines cross. Are these perpendicular lines? These
No.
intersect. but they're not perpendicular. What does it mean to be perpendicular?
They have to have exactly opposite slopes, right?
Well, you're getting warmer, okay? You got about 50% of the way there is what you just said there. But on perpendicular lines are lines that have to intersect, but they intersect and form very special angles to each other. They intersect each other at right angles. This is a 90-degree angle. This little symbol is used in geometry to represent you got a 90-degree angle here, a right angle. Okay, so lines are perpendicular if they intersect each other at right angles. So this would be 90 degrees. This would be 90 degrees, 90-degree angle, 90-degree angle. So 90 plus 90 plus 90 plus 90 is 360 degrees. Do you agree? All right. So these are perpendicular lines. So I'll call this line L1, call this line L2. So if line 1 is perpendicular to line 2, then what must be the case about their slopes? Somebody said that the slopes had to be what? Was it opposites or something? Did you say opposites? There's two things about the slopes of perpendicular lines. Not only do they have to be opposite in sign, but they also have to be reciprocals of each other. Okay. So if line 1 is parallel to line 2, then we would say the slope of line 1 would be equal to the negative reciprocal of the slope of line 2. This is a way of saying that these slopes are negative reciprocals of each other. Let me write that down. Negative reciprocals. Or you could say just as well that the slope of line 2 is the negative reciprocal of line 1. Or there's another way to say that these slopes are negative reciprocals of each other, is to say that their product always gives you -1. If the product of two slopes is equal to -1, that means they're negative reciprocals of each other. So that's what it means. So suppose that a line 1 has a slope of 2/5. What would be the slope of line 2 if it's to be perpendicular to this line? What's the negative reciprocal of 2/5?
-5/2.
-5/2 would have to be its slope. These are called negative reciprocals of each other. So suppose, here's another example. Suppose the slope of line 1 is like 1/3. What would have to be the slope of line 2 if it's to be perpendicular to line 1? So what's the negative reciprocal of 1/3? -3/1 or -3? Okay. Now watch this. What if the slope of line 1 is 0, meaning it's a horizontal line? What would have to be the slope of a line that's perpendicular to this? In other words, what would be the slope of a vertical line to this horizontal line? What's the negative reciprocal of 0? Technically, this is 0/1. Think of it that way. What's the negative reciprocal of 0/1? Well, that would be -1 over what? 0. But -1 over 0 is called what?
Undefined.
Undefined. And that makes sense, because if the slope of a line is 0, that's a horizontal line. And to be perpendicular to a horizontal line, our line must be vertical. Well, what's the slope of a vertical line? Oh, it has to be undefined, because we said that before. Okay, is this making any sense here? All right, so to recap, parallel lines have equal slopes. Perpendicular lines always have negative reciprocal slopes. Negative reciprocal slopes. Okay, so here we go. Here's a problem. Find the slope of a line A parallel and B perpendicular to the linear equation 4x minus 2y equals 10. This is a typical problem you'll run into on Alex. Find the slope of a line that's parallel to this line, this equation, this linear equation, and perpendicular to this linear equation. What do you think the first thing we need to do? What do we need to find out first? Anybody? We got to find the what? We need to find the what? We need the slope of this line. We got to have the slope of this line. Need the slope. Well, how are we going to find the slope of this line? Well, we could put this equation from its present standard form into what form to read off the slope of the line? We could put this into what form?
Y-intercept.
Yeah, so let's put it in the slope intercept form. So therefore, we're going to take this linear equation, we're going to solve for y. Because we want to get this in the slope intercept form. That way we'll be able to read off the slope of this line and then answer our question. All right, so how do we solve for y here? Well, solving for y, we have to subtract 4x from both sides. So I subtract 4x from the left and the right. 4x is drop on the left, leaving me with negative 2y. And on the right, I'm going to flip these around and call it negative 4x plus 10. I'm now going to divide both sides of my equation by a negative 2. That means the negative 4 gets divided by negative 2. And the 10's got to get divided by negative 2. Hence, therefore, my equation now in slope-intercept form is going to be 2x minus 5. Now we're in business because I should be able to read off the slope of this line. What's the slope of this line? What's the slope of this line? I should be able to read it off. My slope is positive 2. That's your slope of this line, 2 or 2 over 1. And of course, that's your y-intercept. Okay, so therefore, we discovered that the slope of this line is 2 or 2 over 1. So if the slope of this line is 2 or 2 over 1, what must be the slope of a parallel line?
Has to be the same.
It has to be the same. So the slope of a parallel line must also be, slope of my parallel line must be 2. Look at my symbolism. The slope of my parallel line must be equal to 2. What must be the slope of my perpendicular line?
Negative 1/2.
Negative 1/2. And we're done with this problem. Everybody understand how we answered that question? So to find the slope of a line that's parallel and perpendicular to this linear equation, first we hammered this in the slope-intercept form, determined its slope, and then we're able to answer the question. What must our slope be if we're parallel, and what must our slope be if we're perpendicular? All right. All right, is this making any sense here so far? Something that you're going to be doing all the time, especially in your first semester of calculus, is writing the equation of a line. So do we know how to write an equation of a line? Right. So we're going to try to write, if I can write it, write the equation of the line containing, suppose my line contains this ordered pair 0, negative 4, and has a slope of 1/3. So my job now is to write an equation of this line that contains this point, in other words, passes through this point, and also has this slope. So how are we going to do that? How are we going to write our equation in x and y? Well, at our disposal, we can use the what? The slope-intercept form. So therefore, I'm going to use the slope-intercept form to help derive the equation of this line that contains this point and has this this slope. Okay. All right. So therefore, using y equals mx plus b, what do I know? What information do they give me about this line? They give me the slope is 1/3, so I can take the slope 1/3 and substitute it into this equation for the slope m, because they tell me the slope of the line. Furthermore, they give me a point that lies on the line. But ladies and gentlemen, what kind of point is this? This is a special point. This is not just any ordinary point on the linear equation that I'm trying to come up with. This is a special point called the what intercept?
The y-intercept.
This is the y-intercept. This is literally the y-intercept because it's a point that lies on the y-axis. So that is the y-intercept, which means that b is negative 4. In for b goes negative 4. That's your y-intercept. So when we make all these substitutions, the equation of my line has got to be y equal to 1/3 x minus 4. And there's your answer. And we're done. So therefore, I've written the equation of a line that contains this point and has this slope. This would be the equation of that line in slope-intercept form. Y equals 1/3 x minus 4. This was a nice problem. The reason why it was a nice problem is because the point they gave us that lies on the line happens to be the y-intercept. That's why it was a very easy problem to write the equation of that line. Do you think we're always going to be given the y-intercept? No, we'll be given maybe some other point that's not the y-intercept. Maybe we should look at one like that. But does anybody understand how I wrote the equation of this line for this problem here? All right, so we'll call this question A, and B then wants us to, or is asking us, can we write the equation of the line that contains these 2 points? And the 2 points are going to be -4 and -2, and the other point is, I'm sorry, and they're also going to tell us the slope of this line is going to be 3/2. All right, so now they want us to write the equation of the line that contains this point -4, -2, and has a slope of 3/2. Is this problem going to be as easy as the last problem? What do you think? Yes or no?
No.
Not as easy, because now the point they give us that lies on our line is not a y-intercept like it was up here. We were lucky up here. This was just a y-intercept. And for B went in -4. This is not a y-intercept. It's just some other point that lies on our line. We have got to find the y-intercept if we're going to write the equation of this line. So to do that, we're going to use our slope-intercept form. So using y equals mx plus b, and using the given information about our line, we're going to show you how to write the equation of our line. Obviously, dropping in for the slope m is going to be 3/2 because they tell us the slope of the line. But this is not a y-intercept. This is just some other point that lies on our line. So generically speaking, I'm just going to call this point just some point xy. Well, if this point lies on my line, then it has got to satisfy the equation that I'm going to come up with. It has to be a solution to this equation I'm trying to write. Well, that being the case, therefore, if it's to be a solution to this equation, I should be able to substitute in for the x variable, the x coordinate of -4. I should be able to substitute in for the y variable in this equation, the y coordinate, which is -2. -2 goes in there. All right, so let's make our substitutions now. So y, which is really -2, is equal to my slope, which is 3/2 times x. X takes on the value of -4, plus my y-intercept of b. So I have to solve for my y-intercept b now. Well, what is 3/2 times -4? That's going to be -12/2. -12/2. But isn't -12/2 better known as -6? Now, how do I solve for my y-intercept b? Add 6 to both sides. And what's my y-intercept? 4. Now we're done. Because now I know the slope of my line is 3/2. I know my y-intercept must be 4. And therefore, the equation of my line has to be y equal to 3/2 x plus b, which was found to be 4. And we're done. This is your answer. This would be the equation of our line that has this for its slope and contains this point. Everybody understand how I just wrote the equation of that line? Okay, all right, I'm going to classwork number 1, ladies and gentlemen. Today is the 10th day of October. I would like you to do this for classwork number 1. I'm going to have you write an equation of a line. So classwork 1, October 10th. I want you to write the equation of the line that contains this point, 3/6, and has a slope of 2/5. And I want your answer to be in slope-intercept form. So make sure your final answer is in the form y equals mx plus b form. Go ahead. That's classwork number 1. See if you can write the equation of that line that has that slope and contains that point. All right, go ahead and see if you can do something with that one. Anybody get this equation written? Feel confident? What would it be? Anybody got it written in slope-intercept form?
I got an answer.
What do you got?
Y equals 2/5 x plus 4 4.8.
4.8. All right, so let's see, 4 and 8/10. What would that be as a fraction? 4 and 8/10 is 4 and 4/5, which is going to be 24
It's
over 5.
24 over 5.
24/5. If you lift that as a fraction. Okay, let's see. We know the slope of our line. We know it contains a point. To write its equation, we're going to use the slope-intercept form to help us out. Therefore, 2/5 drops in for the slope, m. 3/6, if it's a point on my line, must satisfy this equation, meaning that the y-coordinate better take on a value of 6. The x-coordinate better take on a value of 3. Making all these substitutions, we therefore have 6 is equal to 2/5 times 3/1 plus b. We got to solve for the y-intercept. Now, 2 over 5 times 3/1 is going to be 6/5. And now we got to solve for the y-intercept. So b, my y-intercept b is going to be 6/1, subtract 6/5. Common denominator is 5. So another name for 6/1 is going to be 6/1 times 5/5, or 30/5. And 30/5 minus 6/5 is going to net us 24/5. And there's your y-intercept. Therefore, the equation of my line must be y is equal to 2/5 x plus 24/5. Nice job. You were correct. That would be the equation of our line, ladies and gentlemen, in slope-intercept form. All right. Any questions with this classwork 1? Hopefully we are all getting this. Hopefully this is making some sort of sense here. All right. Any other questions about this? Okay, let's see, one last concept in this section is addressing something called the average rate of change of a function with respect to x. The average rate of change of a function f of x with respect to x on some interval AB. Okay. Wow, that's saying a lot. What is all this saying? Let me draw a picture for you and you'll be able to see through the picture what all these things are saying here. Suppose we graphed a function, and suppose this function does not have a straight line graph. Suppose that it has maybe a curve type graph. Okay. Here's a point on my graph. Here's another point on my graph here. And I'm going to call this tick mark on the x-axis A, and I'll project this point down to a tick mark on the x-axis called B. I have some closed interval here on my x-axis. I want to compute the average rate of change of this function f of x with respect to x on this interval from A to B. The average rate of change of this function is going to be, geometrically, it's going to be equal to the slope of this line segment that connects these 2 points on my graph. The slope of this line segment is going to be equal to the average rate of change of my function with respect to x. So the slope of the line segment is going to be equal to the average, AVG short for average, rate of change of f of x with respect to x. There's a quicker way to abbreviate the average rate of change of f of x with respect to x. Here's the notation. Delta f of x over delta x, a vertical bar, and then put the word average. This is a way of representing the average rate of change of the function f of x with respect to x. Very compact symbolic way of indicating that. Okay. Well, this average rate of change is going to be equal to the slope of this line segment. You know what? This line segment has a very special name. When you get into Calculus 1, they're going to call this line segment a secant line, secant. So the slope of this secant line is equal to the average rate of change of this function f of x with respect to x on this interval from a to b. Okay, that's the slope of the secant line. Well, how do we find the slope? Well, to find the slope, we need two unique points on our line. Well, we got two unique, or we need two unique points on this line to find the slope of this secant line, this line segment here. We got 2 points. We got A, and the y coordinate would be f of A. And we got this point B, whose y coordinate would be f of B. So therefore, this point here is going to be a point B, f of B. And this point here, its ordered pair address is going to be A, f of A. And so there you go. I want to find the average rate of change of our function f of x with respect to x. The average rate of change is going to be equal to the slope of my what? My secant line, which by the slope formula, maybe I'll call this point my x2, y2 point, designate this as being my x1, y1 point. Therefore, the slope is y2 minus y1 over x2 minus x1. Therefore, the slope is going to be the change in the y coordinates between this point and this point, which is going to be f of b, subtract f of a. Divided by the change in x, which is to say b minus a, b minus a. And there you go. So this is how you would compute the average rate of change of a function with respect to x, or its input variable, which is x in this case. The average rate of change of a function with respect to x. It's going to be nothing more than the slope of this little secant line, this little line segment that contains the two different points on the graph of our function f of x. All right. So this is how you're going to compute the average rate of change on this interval AB here. So maybe we could look at a specific example, okay? All right. This might seem overwhelming with the symbolism, ladies and gentlemen, but with a specific example, I think all this crazy symbolism will just kind of collapse nicely in your mind as to really what's going on. But, you know, calculus has a tendency to use this rather intimidating symbolism. This triangle means change in x, f of x, versus change in x, okay? This triangle comes from the Greek alphabet. It's called the delta symbol. Delta, that's its name from the Greek alphabet. Delta means change in mathematics, all right? All right, here's an example, specific example. Suppose that I have the graph of a nonlinear function in the xy plane. I have two unique points on the graph, which is the point, this point here is 2, 4, and this point here is 4, 6. And I want to find the average rate of change of f of x, my function, with respect to x on the interval from 2 to 4. So on this interval from 2 to 4, what's the average rate of change of f of x with respect to x? Well, all we got to do is just basically find the slope of this little secant line, this little line segment here. To do that, we find the change in y, which will be the difference in the y coordinates of these 2 points. So that's just going to be f of 4 minus f of 2. But what is f of 4? I'm sorry, this point is 416, not 46. This point is 2, 4, 416. All right, so the change in my y coordinate, or the change in f of x on the interval from 2 to 4, is going to be f of 4 minus f of 2, which is 16 minus 4. When x is 4, f of 4 is 16, minus f of 2 being 4. Divided by the change in x. The change in x is just 4 minus 2. So the average rate of change of this function f of x with respect to x on this interval from 2 to 4 is going to be 12 halves or 6. That'd be the average rate of change, 6. Questions on that problem there? Here's another problem. Suppose that we want to compute the average rate of change of this cubic function, f of x equals x cubed, on the interval from 1 to 2. Well, I took the time to actually graph this third degree function. It is a windy road type graph here. That would be its graph. And we're interested in the average rate of change of this function f of x on the interval from 0 to 2. So therefore, excuse me, on the interval from 1 to 2. So therefore, I'm interested in 2 points, this point right here and this point right here on the graph. And I'm going to connect them with a little line segment. That's my secant line. And the slope of this little secant line is going to be the average rate of change of this function with respect to x on the interval from 1 to 2. All right, so that's going to be the change in y over the change in x. So what's the change in y? Well, what's the value of my function at 2? In other words, what's f of 2? That means you got to put 2 in here. So that's going to be 2 cubed minus f of 1. The value of my function when x is 1 is going to be f of 1, which is 1 cubed. That's the change in y, divided by the change in x, which is just going to be 2 minus 1. That's the change in x. So the average rate of change of this function on the interval from 1 to 2 is going to be 8 minus 1 over 1, or 7. Your answer would be 7. That would be the average rate of change of this function on the interval from 1 to 2 would be 7. Okay. So that's the average rate of change of this function on the interval from 1 to 2. It's 7 for this cubic function f of x equals x cubed. All right. All right, so that's a typical problem involving computing the average rate of change of a function on a particular interval. Again, geometrically, it's always equal to the slope of this little secant line, whose endpoints are the endpoints of the interval in question. Okay. All right, so I think that brings us to an end of that section there. Okay. So, ladies and gentlemen, the last section this afternoon is going to be section 2.5, where we actually apply linear functions to modeling natural phenomena in the real world. All right, so we're going to put these things to use in 2.5, applications of linear functions. All right, now we've seen there were 2 forms for a linear equation. This is called what form? Do you remember? Standard form. This is called what? Slope-intercept form. There is another form for a linear equation. It's called point-slope form. Y minus y1 is equal to your slope m times x minus x1. This can be derived just by using your slope formula. This is called point-slope form for a linear equation. They call it point-slope form because from the equation, you can read off a point that lies on your line. And that point that lies on your line would be the point x1, y1. And of course, m is the what? The slope. That's why we call this the point-slope form for a linear equation. It's another popular form for a linear equation. And using algebra on any one of these forms, you can always navigate to any other form if need be necessary. All right. All right. Point-slope form. All right. That's another popular form for linear equation when trying to apply linear functions to application problems. All right, here's what we're going to do here. We're going to determine if the 2 lines are parallel, perpendicular, or neither. And here are the 2 linear equations. 2x plus 3y equals 7 versus 4x equals negative 6y plus 2. Well, to do that, you have to find the slopes of both these lines. And to do that, you want to probably hammer them both into what? Slope-intercept form.
Can you go down,
I
please?
can't see the second one.
It's right here. I'm sorry about that. All right. So here you got 2 linear equations. We're trying to determine if these are parallel, perpendicular, or neither. So we're going to get both these into slope-intercept form. All right. Now, I'm going to speed things up just a little bit. If you were to solve this equation for the variable y, hammer it in a slope-intercept form, you're going to have y is equal to negative 2/3 x plus 7/3. That equation is now from standard to slope-intercept form. Same thing here. When I solve this equation for y, I'll spare ourselves of the details. So y is going to be equal to, when you get in the slope-intercept form, y is going to be equal to 4 over negative 6x. Okay. Minus 2 over negative 6. So cleaning the second one up here, we're going to have negative 2/3 x plus 1/3. This one is now in slope-intercept form. Ladies and gentlemen, you be the judge. What's the slope of this line here? Slope is negative 2/3. We'll call that maybe line 1. And what's the slope of this line? Negative 2/3. Maybe call this line 2. So what kind of lines are these if the slopes are identical?
Parallel.
These are parallel lines, okay? And we're done with that problem. And if you were to take the time to graph these linear equations in the XY plane, maybe using the slope-intercept form method, you would discover they are parallel lines. How do I know these lines are not the same line now? How do I know they're different lines? You know, a line that's itself is parallel to itself. Do you agree? Technically? Well, no, it isn't, because it intersects itself at an infinite number of points. Well, you can tell these are different lines because the y-intercepts are different, 7/3 versus 1/3. So they're not the same line, but they are parallel because they do have the same slopes. Okay. All right. Everyone make sense there? Now, if the slopes were not equal to each other and they were not negative reciprocals of each other, then we would have to say the lines are neither parallel or perpendicular. That would be the case if you just have lines that do intersect each other but do not intersect at right angles. We would say that's the neither case. Okay. All right, but these were parallel. Okay. I want to go to our textbook here. So I'm going to have to bring up the Am I still coming through? All right, can we see this or not?
Yes.
Yeah.
All right, I'm going to go to page 223 in our textbook. This is jump to 223. All right, here we go. Application problems involving linear functions here. Number 52. Okay, here we go. At a parking garage in a large city, the charge for parking consists of a flat fee of $2 plus $1.50 per hour. A, write a linear function to model the cost for parking P of T for T hours. B, evaluate the cost function at 1.6 hours to interpret how much we're going to have to lay out park. So in part A here, they want us to develop a cost function which is going to be P of T, where P of T is equal to the cost in dollars. T represents what? Time and hours. Okay. So our ordered pairs are the form of T, P of T. That's our ordered pairs, which represent the X and Y coordinates. All right, so it's $2 plus $1.50. Okay. So we're trying to write a cost function here. P of T is the cost in dollars for parking for T hours. And our total cost is going to be our flat fee, which is a one-time fixed fee, plus our variable cost. Well, what was the flat fee? Whether we stay in the parking garage for a minute or for 10 hours, we still got to pay the what, $2. Do you agree? That's your flat fee, your fixed one-time fixed cost you have to pay. Plus your variable cost is going to depend upon the number of hours you stay in the garage. And they say they charge us $1.50 per hour. And so we're going to be in the garage for T hours. So therefore it's going to cost $1.50 per hour times T hours. Spinning these terms around here, we now have a linear cost function here. This is how much it's going to cost us in dollars to stay in this parking garage for T hours. There you go. That would be your cost function there. All right. What would be the slope of this line? You recognize what form this is in? Y equal to what? MX plus B form in general. So what's the slope of my line here? The slope is $1.50, which is slope is a rate. In this case, it's a rate of change of cost versus what time that you're in the garage. $1.50 per every what? 1 hour. Do you agree? Slope is a rate of change. It's a rate. $1.50 per hour. Anything that says something per something is called a rate in mathematics. So $1.50 per 1 hour. That's the rate with which you're going to be charged every hour. What's the y-intercept? How do we interpret what the y-intercept is saying here? The y-intercept is what? $2. Ladies and gentlemen, that would be the cost that we would still have to lay out if we were in the garage for 0 hours. If we were in this parking garage for 0 hours, we're still going to have to lay out that fixed cost of $2. Do you agree? So the cost for parking in the garage for 0 hours is still going to be $2. That's if we basically just enter into the garage and then take right off and exit the garage without staying in the garage. Still got to pay that $2. That's what the y-intercept represents. They want us to evaluate this function at 1.6. In other words, they want us in part B to find out how much it's going to cost if we park in this garage for 1.6 hours. All we got to do is replace T in the definition of this function with 1.6. So what's 1.5 times 1.6? $1.5 times 1.6. That gives me 2.4. So it's going to cost me $2.40. Is that right? Or did I forget to add? Oh, wait, I forgot to add the $2. That's going to be plus $2 more, the one-time fixed cost. So that's going to be $4.40. So to park in this garage for 1.6 hours. And what is 1.6 hours? Well, that's going to be 1 hour and what? Plus 6/10 of an hour? True? So what's 6/10 of an hour? 60 minutes in an hour. That's going to be 6/10 times 60 minutes per hour. 10 divides itself once, goes in 66 times. 6 times 6 is 36. That's going to be 36 minutes. Therefore, 1.6 hours is 1 hour and 6/10 of another hour. That 6/10 of another hour is going to be 36 minutes. So to park in this garage for 1 hour and 36 minutes, it's going to cost you $4.40. And we're done with that problem. Everybody understand what we did there? So we modeled the cost of parking in this garage for T hours according to a linear function.
I have a bit of a question.
Yeah.
So what you did there is you basically transferred, you basically converted from hours to like minutes.
Yes. Well,
Right.
I converted 6/10 of an hour into minutes because I just wanted to know, I mean, if I say 1.6 hours, what does that mean? I mean, we know what 1 hour is, correct? But what's 6/10 of an hour? Well, 6/10 of an hour is going to be 6/10 of what? 60 minutes, correct? Which is to say 36 minutes. Make sense there?
Yep.
Okay. Next one, number 56. 56. For these problems here, they want us to, they give us the fixed and the variable cost to produce an item are given along with the price at which an item is sold. They want us in A to write a linear cost function that represents the cost C of X to produce X items. B, write a linear revenue function that represents the revenue R of X for selling X items. C, write a linear profit function that represents the profit P of X for producing and selling X items. D, determine a break-even point. Okay, so they got us doing everything here. All right, now in problem 56 here, they indicate that we are to lay out a fixed cost of $2,275. Think of this as being maybe the startup cost of our business, maybe just to rent warehouse space, okay, to house our items that we're going to produce and sell, okay? We'll call that the fixed cost. The variable cost, they indicate, is to be the cost of manufacturing one item is going to be $34.50. That's how much it costs to produce one item. The price at which we turn around and sell an item is going to be $80. So this is called the selling price, which is $80. Okay. Now for part A of this question, they want us to write a cost function that represents the amount it's going to cost to produce X items, whatever these items are. Fill in the blank. They could be computers. They could be, baskets, straw baskets, or they could be anything, hats or shirts or whatever we're selling. It don't matter. So anyways, what would be the cost, my linear cost function? Well, my linear cost of producing X of these widgets or whatever you want to call them is going to be a what? A fixed cost plus a variable cost. Well, what's my fixed cost? My fixed cost is this $2,275 plus my variable cost. Okay, if I produce X items, each item is going to cost me $34.50. So if I produce X items, then the cost that I'm going to incur in producing X items is going to be $34.50 per item times X items, because I'm going to produce X items. So this would be your variable cost here. It depends upon the number of items you produce as to what cost you're going to incur. This is a cost you have to lay out regardless. If you produce one widget or a million widgets, you still got to lay this cost out. This might be your initial setup fee for, like I said, maybe rental space or office space or whatever. So therefore, our linear cost function, C of X, the cost of producing X items, is going to be represented by this cost function, 34.50 times X plus 2275. That's your linear cost function. What does the slope represent in the context of our situation? The slope is the rate of cost per every item we manufacture. $34.50 per every item we manufacture. That's what the slope is interpreted as. The y-intercept is interpreted as the initial setup cost, because if you evaluate this cost function at 0, you put 0 in for X, this term drops out. You're still left with an initial setup cost of $22.75. So this is the cost that you're going to have to pay regardless. Even if you manufacture 0 items, you're still going to lay this cost out. Okay? That's your cost function. Now in part B, they want a revenue function. What is revenue? Cost is money we have to lay out. What is revenue? Revenue is money that we bring in. Do you agree? That's the money we bring in. And how much are we going to bring in? Well, they tell us our selling price is going to be $80 per item. So for every one of these items we sell, we're going to rake in $80. That's our revenue. So to write a linear revenue function is pretty simple. Our revenue is going to be $80 per item we sell times X items. That is your revenue function. It's a linear function. So the slope of this revenue function means this would be the rate with which we bring in revenue, $80 per every item we sell. Technically, the y-intercept of this revenue function is 0, which makes sense, because if you evaluate this revenue function at 0, put 0 in for X, you're going to have 0. That makes sense, because if you sell 0 items, you're not going to have any revenue. You're not bringing any money in. So this would be your revenue function. You don't even have to say plus 0. It's understood the y-intercept is 0. All right. The next function in C they want us to develop is called the profit function. Profit, ladies and gentlemen, in the business world, profit is always equal to revenue, money you bring in, minus the money you have to outlay, called the cost. Profit is equal to revenue minus cost. So to develop this profit function, P of X, is simple. We just have to use a little bit of algebra of functions. We have to take our revenue function, R of X, and we have to subtract off our cost function, C of X. Our revenue function was found to be 80X. Subtracting our cost function was 3450X plus 2275. So our profit function for manufacturing and selling X items, the profit we're going to realize is going to be this. We might want to simplify this by distributing the negative sign inside the parentheses here and combining like terms. So what's 80X minus 34.5X? Can somebody dial it up for me? What's 80 subtract 3450X? Combine.
4550.
So 4550X. And then this negative sign is going to go into the 2275. We have ourselves a profit function now, a linear profit function. So for every X items we manufacture and sell, we're going to rake in this profit here. So suppose that I manufacture and sell, let's say 100 items. What profit would I realize? Well, that's going to be 45.50 times 100 minus 2275. So what profit will I realize? That's going to be 4550 minus 2275. And what does that give me for the profit?
2275.
2275. Okay. So do you agree, ladies and gentlemen, if I manufacture and sell 100 of my items, I've made a profit of 2275, enough to cover the what? The initial setup fee? The cost of my business to get it up and running? Do you agree? There you go. So these functions can be very instructive in the business world here. And the last question is, when do we break even? First of all, are there any questions on how we developed all these these functions here? The cost function, the revenue, and the profit function. These are all linear functions.
I have a question.
Yeah.
So is CX always going to be the fixed cost plus the VBL?
Yeah, usually your total cost is the fixed cost plus some sort of variable cost, usually. Okay. You could have some other costs in there. I don't know. Maybe you got like some sort of you have a special tax cost or something, imposed or levied by the government or something. You know what I'm saying? That could be another possibility. But normally it's just fixed cost plus variable cost. All right.
All right.
All right. There's one last question here with regards to this. They want us to find the break-even point. The break-even point. What does it mean in the business world to break even? How do we break even?
Revenue and expenses should be like the same.
That's right. You're right. To break even, the revenue, okay, has got to be equal to the cost. When revenue equals cost, that means we're not making any money, but we're not losing any money either. This is called a break-even point in the business world. So there, ladies and gentlemen, in order to find the break-even point, in other words, to find out how many of these widgets we have to manufacture and sell to break even, we're going to take the revenue function, which is 80X, and we're going to set it equal to the cost function, which we developed to be 34.50X plus the 2275. And now we're going to solve for X to determine how many of these widgets we must manufacture and sell to break even. So we got to solve for X. So how do I solve for X? I'll bring this over to the left side by subtracting 3450 from both sides. Wait a minute here. This should be 80X, shouldn't it? Yeah, I'm sorry. My revenue was 80X. So what's 80X minus 3450X? Somebody dial it up for me. And what does that give me here? So what does that give me?
4550.
So 4550X is equal to 2275. Divide both sides by 45.50. And how many of these widgets must we manufacture and sell to break even? X is equal to what? So what's 2275 divided by 4550?
50.
50. 50 items, ladies, must be manufactured and sold to what? To break even, okay? To break even here. And tell you what, if we were to graph this cost function and revenue function using our graphing calculator, let's see if we can hurry up and do that. I want to show you something cool here. So what I'm going to do is I'm going to try to graph both of these functions on my graphing calculator. So I got to go to y equals my equation editor, y equals, and then for y1, I'm going to type in my revenue function, 80x. Below that, y2, I'm going to type in my cost function, which was 34.50x plus 2275. That's my cost function. My revenue function will be in blue. My cost function will be in what? Red, correct? And I'll tell you what, I'm actually going to also type in my profit function for y3. My profit function was 4550x minus 2275. That's my profit function. Let's graph all these functions and see if we can see any of these. Well, we got to work on our scale a little bit here. I'm going to notice I go to window, my x-axis just ranges. Hold on, I don't think this thing's done yet. It's still working. Okay, this scaling's way off. I'm going to have my x minimum value be 0 and my x maximum value be like 100. And I'm going to space these by maybe 10 units apart on my x-axis. Y-axis is going to run from 0. Remember, y is going to be revenue or profit. Maybe we better go to like 2000. I don't know. Let's just look at this scaling here and see what happens. Let's see if we can see our graphs here. Okay, so we're still having a problem here seeing our graphs, so we have to, configure. Well, there's the profit function, and what else do we got here? Do you see the red graph anywhere? 50 items. Let's see, 50 items. What was my y? My y is 0 to 2000, right? Oh boy. All right. So we're having a problem with our scaling here. Maybe maybe you go to Zoom and do a Zoom fit. That sometimes, starts getting you in the ballpark where you can start to see your graphs a little better. Zoom fit tries to configure X and Y axis so you can start to see these graphs. And let's see here. Okay. All right, ladies and gentlemen, how do we interpret what we're looking at? What was the blue graph? Do you remember? Blue was what? Revenue. Red was cost. Black is profit, correct? All right, so notice where the blue and the red graph intersect, that's the point of intersection. That's where we break even. And when we break even, our profit, the black graph, is running through the x-axis. So the profit is $0 when we break even. It makes sense. Now, wouldn't we like to find this point of intersection, the break-even point? We can do that. Go to calculate, second trace. Go down and use the intersect function. Let's find the point of intersection between our red and blue graph, the revenue and the cost function. There will be my first curve, hit enter. There's my second curve, hit enter again. There's your break-even point, 50, 4,000. So ladies and gentlemen, if we manufacture and sell 50 of these widgets, we will break even with a revenue of $4,000 and a cost of $4,000. And my profit will be $0 down here. You see that? We broke even. Is that making sense there? Now, what if I manufacture and sell more than 50 items? What function exceeds what function? Notice if we go to the right of x equals 50, my profit function black graph is above the what? X-axis. That means our profit's going to be positive. That makes sense because above x equals 50, my blue graph, my revenue is above the red cost function graph. That means my revenue is exceeding cost if I manufacture and sell more than 50 items. If I manufacture and sell less than 50 items, it's my red cost function that's above my blue revenue function, which means I will be laying out more money than I'm bringing in. That's why the black profit function is below the x-axis for values of x less than 50, because that means our profit is negative. We're losing money. Is this making any sense here? All right. Look at that one. Let's see. We're almost out of time here. Number 61. Okay, this problem here, let's see here, or let's use this one here. This one's interesting here. Caroline adopted a puppy named Dodger from an animal shelter in Chicago. She recorded Dodger's weight during their first 2 months. The data in the graph show Dodger's weight, Y in pounds, versus X days after adoption. Horizontal axis, the number of days after adoption, and the vertical axis represents the weight of this little puppy in pounds. All right, they give us 2 points on this line, 0, 11 and 40, 22. The y-intercept is 11. Can anybody interpret in plain English what the y-intercept is saying? What is 0, 11 saying in the context of this problem? Anybody? It's saying when we first adopted Dodger, his weight or her weight or whatever, the puppy's weight was 11 pounds. Does that make sense? When we first adopted Dodger. 40 days after we adopted Dodger, the weight went up to 22 pounds. Ladies and gentlemen, they want us to use these 2 points to write a linear function that models the weight versus the age of this puppy. So how do we do it? Well, they give us 2 points on this line. They give us 0, 11, and they give us the other point as 40, 22. So how do we write the equation of this line here, given these 2 points? Well, I'll call this my point x1, y1, and designate this as being my second point. We need the slope of this line first. Using the slope formula. The slope of this line is going to be y2, which is 22, minus y1, which is 11, over x2, which is 40, minus x1, which is 0. Therefore, the slope of this line is going to be 11 over 40. And how do we interpret what this line is saying here? Well, ladies and gentlemen, it's saying for every 40 days after we adopted Dodger, for every 40 days we have this puppy after adoption, Dodger will put on 11 pounds. So the rate of weight gain for the age of this puppy is going to be 11 pounds per every 40 days. Everybody see that there? That's how you interpret the slope, 11 pounds per every 40 days. Okay. Now, one of these points is a y-intercept. It's not this one, but here it is. This is our y-intercept. So we can write the equation of this line. So the weight of Dodger, W, is going to be equal to my slope, which is 11/40, times the number of days after adoption, I'll call D, plus the y-intercept, which is 11. We have modeled that ordered pair data as a linear function, which models the weight of our puppy versus the day after adoption. Everybody see that there? Okay. All right, and then you could use this function to make predictions. For instance, 30 days after we adopted Dodger, what would be the puppy's weight? Well, you just have to put 30 into this function for days. So what's 11/40 times 30 plus 11? Well, you'd have to get on your calculator and dial that up. And what would that give you for Dodger's weight? 11 times 30 divided by 40 plus 11. Dodger's weight would be 19.25 pounds. And there you go. That would be the weight of Dodger 30 days after we adopted Dodger. Okay. All right. So you can model ordered pair data according to a linear equation, and then use that equation to, make predictions or forecasts. And the process of fitting a linear equation to ordered pair data, ladies and gentlemen, has a name. It is called linear regression. Linear regression. And unfortunately, I did not get to linear regression. But linear regression can be performed on the calculator, and I will show you an example in your textbook that illustrates linear regression and how you can model ordered paired data according to a linear equation. Okay, so like here's a data set where we could call the number of calories that a hamburger has as the X variable, and we could designate the cholesterol in milligrams being the Y variable. So we have a bunch of ordered pairs here, X comma Y, X comma Y, X comma Y. And there is a way of then fitting a linear equation to these ordered pair data points. That's called linear regression. That's something that you would study in statistics here at Mott. But by performing linear regression, we can crank out a linear equation or a linear function that models the relationship between the number of calories a hamburger has and the number of cholesterol in milligrams that it has. That's called linear regression. And there is an example in our textbook that I will draw your attention to study. It also shows you the keystroking you can do on your calculator to actually crank out that linear regression equation. All right. So the idea behind applications involving linear functions hangs out in this section here. All right, so let's see here. So we have that there. Now this data here, one last thing here, this represents the barometric pressure of a hurricane versus the wind speed the hurricane can muster. And notice as the pressure increases, the wind speed decreases, okay, and vice versa. They give us 2 points of interest here that they collected out in the field. When the center pressure of a hurricane is 950 millibars, the central wind speed was 110 miles per hour. When the pressure rose to 1,000 millibars, the center wind speed of the hurricane decreased to 50 miles per hour. I'm assuming these are sustained wind speeds. They want us to write a linear function that models this ordered pair data here. And to do that, we could maybe call our X variable the pressure variable, and the Y variable, we could call it the wind speed. Okay, so we have 2 ordered pairs here. We have 950 comma 110, and our other ordered pair is 1,000 comma 50. If you have to go, ladies and gentlemen, that's okay. You can cut out. I'm going to finish this example, and it will be part of the video. Okay, that's the beauty of having this baby on virtual here, is that I can go longer with the lecture. You guys can split if you want, but you'll be able to see this at the tail end of the lecture here, the video. So what I'm going to do here is I'm going to call this point my X1, Y1 point. Well, first of all, it'd be nice if we could even see what I'm doing here. And I'm going to call this my X sub 2, Y sub 2. So I'm going to model this wind speed versus pressure data according to a linear function. P is pressure, W is wind speed. P is my pressure, which is my independent variable, my X variable. The wind speed is my dependent variable, which is the Y variable. First, I need to find the slope of this line. So the slope is going to be found by taking Y2 minus Y1 over X2 minus X1. Feeding the values into the formula here, we have 50 minus 110 divided by 1,000 minus 950. 50 minus 110, I believe, is going to be negative 60. 1,000 minus 950 is going to be 50. How do we interpret what the slope is saying? It's saying that for every, remember Y, ladies and gentlemen, is the wind speed. The X variable is the pressure. So this is saying for every 50 millibars that the pressure rises in a hurricane, the wind speed decreases by 60 miles per hour. So this is the rate with which the wind speed decreases in a hurricane per the number of millibars that the pressure in the center rises. Okay. I mean, that makes sense because the lower the pressure is in a hurricane, the deeper, more powerful of a storm it is, the stronger the wind speeds. As the hurricane starts to fill in, meaning the atmospheric pressure starts to rise in a hurricane, the hurricane weakens and the wind speed decreases. All right. All right, so now we know our slope, and hey, can't I simplify this slope down to just -6/5? That's saying for every 5 millibar increase in pressure, the wind speed decreases by 6 miles per hour. That's how you interpret what the slope is saying. Now to write the equation of this linear function I'm trying to develop, unfortunately, none of these qualify as being a y-intercept. So I have to just choose a point. So I will choose a point, and let's say that I go with the first point here, 950, 110. And I know my slope is -6/5. Ladies and gentlemen, you can use the slope-intercept form to write the equation of this line like we did in previous problems. But I'm going to use the point slope form because your author wanted us to kind of use it in this section. So I'm going to use the point slope form to derive this equation. And the point slope form is going to be y minus y1 equal to your slope m times x minus x1. That's called point slope form. So this point that I chose is going to be my point x1, y1. Now we just drop things into point slope form. So my equation is going to be y minus y1. y1 is going to be 110 equal to my slope, which is -6/5, times quantity x minus x1. x1 is 950. And there we go. Now, if you want to get this in the slope-intercept form, because this is called point slope form, all you got to do is solve for y. So here we go. I'm going to get this in the slope-intercept form. First, I'm going to distribute the -6/5 inside the parentheses here. So we got -6/5 x. And what's -6/5 times -950? Five does divide into 950 evenly here. So that is going to be a nice integer here. So we're going to have -6/5 x. 5 divides itself once, goes into 950, 190 times. And what's -190 times -6? Gives me 1140. All right, so this is plus 1140. Finally, to solve for y, we add 110 to both sides, and we have this thing in slope-intercept form. Therefore, y is equal to -6/5 x plus 11250. But ladies and gentlemen, my y variable was really called the what? The wind speed variable. So the wind speed is going to be equal to -6/5 times the pressure of the storm plus 1250. We have modeled the atmospheric pressure versus wind speed of a hurricane according to a linear function. There you go. And we're done. Okay. And that ends the lecture, ladies and gentlemen. So if you're still online and have any questions, I will hang on the line for you. If not, have a great day, and hopefully I'll catch you in a couple days. Okay? All right.